So I'm going to share the whole desktop. I hope you're seeing the right stuff. What's visible now is the terminal where I'm typing right now. Is that what you guys see?
Yes.
Thank you. All right. So let me also show you. I mean, that's what you could get. You can either, as we said yesterday, you can either visit this website here. So let me. You can either visit this website and find exactly the same files we have here, or just a Git clone it. And if you do it, what we're going to obtain is, let me go one level down. We're going to obtain is what you are seeing now is the screen, which is a folder with presentations, some old ones, some recent from this workshop already, and tutorials for a number of versions from ALF. And the one we have been following is the development one, so the most current one. And what you care about this here is, of course, the tutorial itself, which is a PDF file. And today we're going to be taking a look at that, a folder called solutions. That's going to be something we're going to take quite a look today. Yesterday, what we saw, what constituted the most of the introductory tutorial was in the notebooks that are available here. They're also available in PyAlf, so it's a bit duplicated here, so it's easy to get. But let me finally open the tutorial. And make it a bit bigger so that it's visible. So ALF now should be installed, so we don't want to worry about that. We should not need to worry about that now. Also, the part from yesterday, of course, is passed. And what I want to take a look at today is actually very much the opposite of what I did yesterday. Yesterday, you had barely seen anything about how ALF works, about its real implementation. And we were happy to treat it as a black box. So all we did was essentially to run some prepared notebooks, some notebooks that were there, and one command after the other, and just looking at what happens, at what is the output. Even the exercises constituted for the most part are actually exclusively changing the value of some parameters, or at the most introducing some parameters, and seeing how it changes the output. Right? That's valid. That's good. But after the couple of ALF basics talks, so the implementation talks we saw already, and after this tutorial, before we can start working on it, we're going to have yet another one. And after the explanation I got from how the theory can be seen, and also the overview Jonas gave yesterday, I think we're more than prepared to actually, as is written there, get our hands dirty and indeed open the code up and change it. Okay, so that's what we're going to be doing today. So what I'm going to show is really just the presentation of the exercise and how it can be solved. Even though I don't want to sound scary for those who don't know Fortran or don't like it, or for those who don't even code that much, it's actually not. We try to make it as smooth as possible. We have only 3 exercises, of course. The difficulty increases, so it can be a bit steep. But I'm going to be concentrating a lot on the first exercise, going really quite slowly through it, so that it's actually helpful. We have a number of Hamiltonians. You can write a Hamiltonian from scratch, obviously, if you know what you're doing. But we also provide the template. That's a recent addition to our our repository, the template Hamiltonian. And we also have had for already, since ALF 2.0 is this Hamiltonian here, the plain vanilla Hamiltonian. It has been written with the explicit purpose of teaching how to use ALF. So we took a bit of the bells and whistles that some of the Hamiltonians have. we avoided to some degree using predefined structures, because what are those predefined structures? They're like, they include those predefined observables, for instance, or predefined hopping and so on. So they are very helpful when you want to implement something new, but when you're trying to understand what's going on, they can be a bit opaque. They can make it a bit harder to understand what's going on, forcing you at the very least to open a number of different files and understand when one is called and what's used from it and so on and so forth. So we try to make it a bit simpler and only in a single file to some degree, exactly for this tutorial actually, so that you can use it, and that's what you do in all three exercises. You use this Hamiltonian file as the starting point for solving the exercise. You see, and we're going to take a look at how it looks. We're going to take a look at it. So I was here in the tutorial folder. Let me go to the ALF folder. So here are in the ALF folder. I'm going to go get out of documentation. I have many things here that has already been presented, so I'm not going to delay myself here. Let's go to the prog, arguably the most important folder here. It has all those predefined things and other modules. But what I'm interested in showing you guys is inside and gals is inside the Hamiltonians. So inside the Hamiltonians, as I said, you have the template, you have a number of Hamiltonians that has already been implemented, such as Condo and many others. But we care about now the plain vanilla. So I'm gonna just open it and take a quick look together, together with all of you. And I'm obviously not going to go line by line. I just want to have a very gross, a very simplified view of what's going on here. So all of that is of course not interesting. If you want to just understand what's going on, it's important, but not interesting right now. At the beginning, you have the variables explained. You can have more extensive and coherent explanation from the docs, and you can also look yourself in the code to see what's going on. But it's a bit clear that the quickest way of looking, okay, so what again is this variable, or how big is it, or what does it do? Then you can take a look here at the header of the file. This is, by the way, the Doxygen documentation, some comments that allow some documentation to be automatically generated. I have that on our website. So you can look at the header to make sure of what the variables, what those abbreviations mean. Okay, so then we start with the real program. You see it's called Hamiltonian. You see it better here. No, you see it better here. It's called Hamiltonian. All of Hamiltonians start like that. We defined it. And then Herbert Plain Vanilla and S mod. That stands for submodule, which means that it's a module based on another module, for to say so, simplifying a bit. And it's based on the Hamiltonian name. Okay, so there are some predefined stuff that we are going to use. Of course, I don't want to go through the very basics of matrices, of defining matrices and the matrices multiplication and stuff like that, right? So what we do here is really especially saying that, okay, how it's going to be called, of course, what are going to be included here. You defined default values and a few of the parameters that you need for this model, in this case, the Hilbert plain vanilla. Okay, here we start, as the name says, parameters. So those are parameters for the lattice. Here are parameters for the model itself, right? Okay, and that's essentially it for this part. Then comes the subroutine that sets the Hamiltonian. To a great degree, it's just going to be calling some other variables, some other routines, and writing information. Here's the part where it's calling other routines. So it's calling hamlattice, which is in the same file just down there. It's calling hamlet and hamhop and hamv. Okay, and some basic definitions right here, as well as the throttle length. And as I said, writing some information. So that's the info file I have been mentioning every now and then that you should look when you run ALF. You should take a look at what's written there. So as you see, it's going to be populated in part by the by the module defining the Hamiltonian. So, and the one that has actually been compiled. That's why it's so important to have this here. So this is not important to you. It's always the same. You don't mess with it much, maybe a bit if you introduce something new. Okay, so that's it for ham set. And then the lattice. Nothing to say here. It's already been explained yesterday. You have those base vectors, and so nothing really to say here. It's already been explained. You don't have to worry about that. The hopping is going to be explained in detail later on, but you can if you want to take a very simplified view on it, you can see that you are defining something here that's going to be, let's say, the intensity of the hopping, and it's defined by this variable here, ham_t, and then you have this for x and for y only if you have 2 dimensions. If you have only one, then this does not run, right? It's based on some operator. That's the base. That's the kind of the most basic unit in some sense for defining everything in ALF. I mean, in quantum mechanics in general. And here's not different. But it's good to take a look at it. So here are defining hopping, and apart from the stuff that is essentially only dependent on the dimension and other general things, what you have here is that this ham_t is what is really something that could be changed. Yes, you have chemical potential, but we're not going to worry about that right now. And the trial wave function has been already mentioned today, is if you want to use the projective code, then you should provide some initial wave function, which again should overlap with the ground state in order to be able to reach it after running. Okay, and then you come for when you define the interaction. So again, it's some interaction operator. It has its parts, which I'm not going to explain because that does not belong right now here. And finally, to the observers. That has been shown in some detail by Francesco today. So I'm not going to now go through it because I'm going to show again this file in a minute, and then I can, but then with a specific goal in mind, then it's going to make more sense. But after defining the observers, we're going to have the observers. After the scalars, we have those here, and after those, correlation-like stuff and ring function, you have the time displaced ones. Okay, so the observers come kind of 3 times, one for each type. Okay, so that's and that's it. It's the end of the file. So here you define all the Hamiltonian using a modest amount of predefined structures. Okay, so back to our tutorial. Once again, that shouldn't be necessary. You should not have to worry about installing it if you do the instructions nonetheless here. And what is our first exercise? We wanted to generalize the hopping so that it can you can have different values when according to whether you're going to the x or the y direction. Okay, so we're going to have ham_t x and ham_t y, for to say so. And so that's the base problem. And we since it's a tutorial and not a list of exercise, we essentially tell you step by step what you should do. And I'm going to go through those now. So as I already made clear, the file I was just showing you right now, this vanilla submodule, is the one you're going to start with. So in principle, you should copy it. You can find it in your ALF directory prog Hamiltonians. And the first step is to change not actually the submodule, but to do it first so that you don't forget, to change the parameters file. We can again take a look at the parameters file. So let's go back to ALF. So I'm going to get out of Hamiltonians, get out of prog, and go to the scripts and parameters files and go to the start folder. And here I have this parameters file, which among other things, this has already been shown by Jonas too. So I just want to remind you of the parts that define the models. So here's the plain vanilla one. As you see, it includes the hopping parameter. And now we wanted to generalize it to having hopping parameters, to have different values for different directions. So in this parameters file that I was showing right now, you should introduce hem ty. We want to rename hem t to hem tx. We leave it as it is. At least here in the example, you can do, of course, any way you want, just so that the number of modifications is not as large, but it doesn't really matter. So add this there to the parameters file. That means you open the file with any editor you want, and here in the namespace where you give the parameters for the Hubert plain vanilla, you're gonna add another line that's very similar to this one. The only difference is gonna be that there's gonna be a y after this t. Okay, this is the first step, trivial enough. And now come the actual modifications to the code. That means changing the Hamiltonian actually. So you can look for the declaration. So because in Fortran, especially the way we do it, you have to declare the variables. That's just to avoid some programming mistakes. So you have to declare this variable, say which type it is, and so on. You don't have to know Fortran to do that. Just search for where hem t is declared and do a similar declaration for hem ty. Okay, so I have to do this declaration. I'm gonna show those changes again in a minute, so you don't have to try to imagine right now how it's done if it's not clear yet. I'm gonna actually show it to you. So we declare the variable. You should include it into the namespace that has the variables for this model. It's essentially the parallel change that we have to do to the parameters file. So this variable has to be present in the parameters file, and the program has to know that it must read it. That's essentially what it is about. And you have to modify, and of course, that's the key modification for this exercise. You have to modify that routine in vanilla called hem hop. The modification is in that loop that takes place only, this if here is not a loop, that if block that takes place only if you have 2 dimensions, which in this case you definitely want to. And even though we commented out the 2 lines and added 2 lines, if you pay attention, the only change taking place is here. So all I'm saying is that now I want the operator, the translation operator, the hopping operator, that related to the y coordinates, should be defined not by the hem t but by hem ty. So the actual change in the code is to add a y in those 2 places down here. If you want to use MPI, you should take a look at those MPI broadcasting commands and broadcast this variable too, right? That's a side comment, but one that might be important in case you decided to use MPI and then suddenly does not work, and you have to do that. And that's it. That's it for this exercise. And now comes the point where I'm going to show the changes once again, because we do include solutions to the exercise. So I'm going to go back here to the tutorial folder and get out of this start. Actually, I'm ALF, so let me go back to the tutorial. Here we are. And I have the solutions folder, and I'm going to go to it. I'm going to enter it. I'm going to change to it. And I have another folder, one for each exercise. And if I go inside of the exercise 1, what we're going to see there is the original Hamiltonian plain vanilla. It's here just in case with time we have some change in the repository and it's not yet updated to the tutorial, so it's good to have the original here. And the plain vanilla modified so as to solve the exercise. So these are the 2 things you might want to take a look. And if you look at the start directory provide, you have the parameters, the parameters file already, since it's inside of the solution, already with the necessary with the necessary variable added it to the namespace, and it's here. Okay, that's all there is to this part. And add the solutions. In case you want to make sure if you got everything that had to be done, if you did all the modifications, or if you are stuck, or if you just are curious. Anyway, one possibility, of course, is to use any Diff Viewers, so any program you have there that can highlight the difference between two files and compare the original vanilla Hamiltonian with the solution, and then you're gonna get some view like that where it's highlighted the difference. So if you look at our solution, we highlighted our solution Hamiltonian. We point out every modification. We remark with the comment, modification for exercise 1. Okay, so here we are adding that the variable that has to be added, like in the beginning of the code, you have to say, you have to define all the variables you want to use in it. Then we have our second modification, which is, I did not mention that, it's not mentioned explicitly, it's not mentioned in the tutorial, but that's why I said before that you might want to do something, which is to do something about it, which is about the information that is printed into the info file. So it's good practice to keep the info file as useful as possible, to include this new parameter in the output that goes to it. And that's also going to help you when you run the code to make sure that you did compile and run the version of the vanilla that you wanted, the one with this modification. You just have to look for this, the value of MTY. The other modification is the one that's printed fully in the tutorial, in the PDF we were seeing a moment ago, which is to say that the y coordinate is now defined. The hop in the y coordinate is now defined with its own parameter and not using the same as for x. And here is the same modification for the trial wave function. So we don't even mention that because you are not asked to run the codes in the projective mode. But if you wanted to, of course, you also have to make the similar modification in the hopping for the trial wave function. And that's it. Okay. So that's something you can use in any diff program you like, some difference between files program you like. And if there is, and that's really about it for the first exercise. That is the part A. Okay, no, there's one last thing, which is also here we provide those three files here. What are they? So the first, so this one is a GNU plot script to generate a plot. The sort of plot it should generate is just exactly the one that is in the it's refusing to increase. Okay, that's in the tutorial itself. So I'm gonna come to it in a sec. It's this one here, and if you want to use this GNU plot script, you should of course know how to prepare the data so that it can understand the data and plot it correctly. And that's why we offer the data the data file as it should be read. And important here actually those spaces. You need 2 lines between the different sets of data. But honestly, I'm not going to go any more into the detail. That's really only for the interested people, and we can talk more about that if there is interest later on. What's going on here is actually very simple. You can run the code for some value of the parameter. So now which parameter we're talking about, of course, is the MTY. And one thing you can do is to try different parameter values. So of course, when the ty is equal to 1, and that's the value that you took for the tx or just mt, you have the situation that you had originally, so no difference actually. And what is being plotted here is the spin correlation functions, so that you'd get from the spin t, so the total spin ec jr file. So that's the file you should look for, looking for this data here if you want to, when you want to compare to see if it's running adequately. And what essentially you see is that you have an exponential decay once the difference between those hoppings is high enough. Okay, it refers to that paper. I mean, it's strongly linked to that paper that is maybe the first project that Faka presented today. So if you were interested in that paper, that could be already in that project. That's already a start, a starting point, a way to play a bit with it. Not for real. I mean, you're implementing something that already exists in ALF, but you can get a better feeling to it if you after doing this exercise. So again, what's being plotted here? What the information I got from this file, which is the correlation, the spin-spin correlation for different values of hem ty or this ty is written here. Okay, the values for the other parameters are given here. So you should be able to reproduce this picture kind of easily. If you don't want to worry about or don't have the time to worry about the GNU plot script or plotting it using Python or whatever you want, you don't have to. You just can take a look at those values here. Like, okay, so that's around the minus 0.4 for the first one. You can just take a look at those values or in those values from this file that you provide and see if they are close enough. Okay. And the B part and the other part, that's a bit more of a I will not call it a challenge, but that's different. That's really different. Then you'd be trying, if you want to do this exercise, the idea is actually to simply do the same changes that that are listed before, that we just saw now, but not to the vanilla, to the Hubert plane vanilla submodules, to Hamiltonian, but to the Hubert Hamiltonian. So the one that's actually used usually when you want to simulate the Hubert model using ALF. To do here, so that you can use this, you can set this here and have a different symmetry, in your model and SUN, and see what changes when you do that. Okay. Any question about this exercise or how to proceed in general? Okay, so if not, we can go to the second one. So in this first one, we just got the model and generalized it slightly, made a simpler generalization. Second exercise, we want to define a new model. That's the TV model. I'm not going to go through the explanation here. We don't have that much time. It's the TV model. A very important remark, though, is that the TV model is actually already implemented. So when you try to solve this exercise, be careful not to use the implementation that already exists, because otherwise it's not an exercise. And be very careful to avoid naming confusions. So what you find in the Hamiltonians folder is TV, just TV, Hamiltonian TV. So the namespace is also TV. What namespace? I'm gonna once again show you what I'm talking about. In the parameters file, you have this namespace here. The namespace is what comes here, and before this is slash. Here are all the variables that we're defining and setting their values. And here you have this var TV namespace. Don't use that. You don't want to do that. The exercise is to modify the plain vanilla so that it becomes the TV model. Okay. So so if you change the namespace from var Hubert plain vanilla to TV, then you can follow our suggestion and use T underscore, where is it? I'm sorry. Oh, here it goes. T underscore V instead of TV. Use whatever you want, just don't use plain TV because then we're going to have some possible conflict with the TV that's already defined. Okay, so once again, we're going to get the plain vanilla and construct the TV from it, the TV model from it. Okay, one nice advantage of having that is that it provides a direct way of checking. You just can change the model, change the parameters file to say that you want to run not your implemented TV from vanilla, but the one included in ALF, and see if you get the same results within the statistical error. So this is the task, and how do you carry it out? Once again, you start with vanilla, with the plain vanilla submodule, the plain vanilla Hamiltonian. Or to be more exact, you first change the parameters file, because if you leave it to last, you might forget it. So let's go back to the tutorial. And now I'm not in exercise 1. I want to go to exercise 2. So this is the folder with the solutions and exercise 2. And here it's we have a very structure similar to the folder of exercise 1. So we have the original Hubert plain vanilla, the modified Hubert plain vanilla. We have a script for plotting if you want to reproduce the plot that you see in the tutorial. The plot is again here, and the data, if you want to take a look at the data alone, or if you want to see how it should be formatted. But here what I wanted to see now is the parameters. Here I even have the parameters and the parameters original. So let's take a look at how the parameters file is changed to solve this exercise. And here, oh, that's for the Hubert plain vanilla. Okay, so we are comparing with so this modification is not the one you should have to worry too much about. It's just if you run Hubert or Hubert plain vanilla, you obviously want to run the one that you've been changing. Modifications in lattice are optional, so you don't want to worry too much about that. Also, so there are some spurious modifications here. I apologize for that. There should not be. So you have some modifications on the quantum Monte Carlo parameters as well. So here we're asking for a larger number of sweeps, so it's going to take longer to run, but it should be fine. Still, it's not too much. You have more beans. Okay, but you have okay, no one mentioned that so far, so why can't we see it now? The CPU max is usually at 0. That's what you have here in the original, which means that it's just going to run for as long as it needs to fulfill the number of sweeps that you asked. But you can put a limit in hours. So 03, this should be 5 minutes, if I'm not mistaken. Yeah, anyway, if you put 05, that's gonna be half an hour. If you put 01, that's gonna be 6 minutes. So that's gonna run for very short. And here the only modification that actually is relevant to the exercise, which is we are commenting HAM_u and introducing a new variable called HAM_v_int. So the interaction, we have a new interaction being defined here. Okay, so that's the only relevant modification. You even see that the other modifications have not been. Oh, they do have because yes, because a very important detail that I'm going to show immediately. It's very important. I want to go back to the tutorial, and I should have said that in the beginning. We want it's in the title, but I did not say it. It's not just the TV model; it's the one-dimensional TV model. Okay. So that modification is indeed important because by default we have a 2D Hubbard, and here you want to have L2 equal 1. So in one direction, in one dimension, you're going to have just one side. So you have a line of sides, and because of periodic boundary conditions, you have a ring. So that's what's going on here. So it is actually important. So this is actually an important modification indeed. All right. So I went a bit ahead of myself by showing the parameters file before telling what should be done. But let's start with the steps. Add this namespace to the parameters file. We have it open right now here. That's not what's being done. Look at that. I just kept the plain vanilla. That's okay. You can do that. So what are the possibilities? You can copy plain vanilla and you change its name to t_v or any other name different from tv. Or you can just keep the plain vanilla and do the modifications that you want to. It doesn't really matter as long as you are consistent. Once again, I say ignore this tv, which is for the present implementation. And you have to change hem_u to hem_v_int. That's what we showed already before. And then, like before, you go. Now we're going to be talking about the Hamiltonian submodule, so really defining our new model. And the first step is a procedural run. Declare this variable so that the compiler knows you want it to exist. Either use the same namespace, Hamiltonian vanilla, plain vanilla, or declare a new one. If you declare a new one, you can just copy from the vanilla and change and perform the changes. Important here, since we're working with spinless fermions, the number of flavors is just 1. If you want to use MPI, do include this change from hem_u to hem_v_int in the broadcast parameters as well, broadcasted parameters as well. We can show that in a sec. And finally, you're defining a new model, right? So how do you go about it? We saw already at least twice how the sort of things work. And today we're going to have, just after this tutorial, before you can have the time to work on it, you're going to have a talk specifically about that, about models in ALF and how to create your own model. So I won't detail any of that. We are just going to say that this model here, which is the one we want to implement, translate like that in the code. So it continues on this side here. Translate like that in the code. So I'm not going to explain it because it's going to be explained by someone else in 20 minutes. It's just you have to put it there. Right now it's just a lot of code that you know should correspond to this operator. Good. And you have to update the observables as well, right? And some of these updates are really trivial since you eliminated hem_u, or you could say it renamed the interaction from hem_u to hem_v_int. You have to make the corresponding change in the routine. You have just one dimension, so one flavor. So that's why this calculation changes like that here. And here you have the observables. Perhaps you remember. I'm gonna talk a tiny bit more about the observables once you open the files, both files. Which we're gonna do probably right now. Again, you can look at the solutions, which is what we're gonna do right now. Yeah. So this is the difference of the parameters file, and I want to now look. I want to look at the original plain vanilla and the solution for the exercise 2. And we're going to see the changes. So here we are defining the variable, letting it know. We're just declaring it. We're declaring the variable. We are changing, right? This. So here's more than you need to solve the exercise, but it's just a good practice. It's just being careful. So that's trying to make it more user-friendly. So this is the modification that really has to take place. So you have one flavor, not 2. And here's just a nice foolproofing, which is if you forget that you're trying to define this model only for one dimension and you actually set L2 to something that's not 1, then the program is going to stop and give you an error message. Okay, so remember the TV model is implemented only for one dimension. Okay, that's what's going on here. We don't mention that in the tutorial because it's not strictly necessary, but since it's here, let me explain it to you. The other change is conceptually simple, and also in terms of programming, it's simple. You're just removing hem_u and including hem_v_int, and then go on. No change, no change. You need I2. It's you need a new integer variable, so you have to declare it. That's all there is to it. Change change the call to the operator. Again, I'm gonna let that to be explained later on. And this is that whole block that we have explicitly in the tutorial. This block here is this block here that you see. And you're gonna have, and here's what I said that I was going to explain better now. So about the observables, which Francesco explained. So the only change from this line to the one below is from 5 to 3. It has to do essentially with the reduction in the number of dimensions from 2, possibly 2 to 1. You don't have to worry about spin in XY direction and total spin if you only have one dimension. So we don't allocate memory for 5 observables, only for 3, and we also comment out those observables we don't need anymore. So it's not really conceptually relevant here. And then we do the same for the equal time correlators, and we do the same for the, at least I'd expect, oh, it's gonna come later on. And here comes, yeah, these are the observables. Yes. The change that we also pointed out in the tutorial just a moment ago, it's being implemented here. And once again, here it looks like there are more changes than there should be, but that's in part because it's been written in a different way. It's just okay. That's together this light implementation difference. I apologize. So it's a bit wordy. The diff output is a bit wordy than it should be. And the last difference is once again just the number of observables reduced from 5 to 3. That's what you see here, from 5 to 3, and corresponding to the rest as well. And the same for the time displaced observables. All right. Good. So what's the B part of this exercise? You can try to take a look at some interesting physics. You can try to take a look at the phase transition. Here, what essentially you have is if the interaction is strong enough. So I mean, the nice explanation is here. I'm not going to read it to you, but essentially, if the interaction is strong enough, you have longer range correlations. Okay, so here we're looking at the density correlation over space, and for v_int equal to 2.5, you have those waves, these density waves here, and for smaller values, especially 1, then it decays very fast. So you can see this phase transition. You can see this phase transition from the model just by running with the 3 different values of v_int. And just as before, you have the data, you have the data, the example data that you should get from this for reproducing that plot. And those like want to use GNU plot, you also have the GNU plot script. And one thing that I should mention, it's not documented because it's not really supported, but you're gonna see it exists. So this is a really simple script, bash script, which does part of the work of converting the data as it comes out of ana.out to the format that's more similar to the one that GNUplot needs. Okay, you can take, so it's just to make it less boring, the work of reproducing the plot if you want to, because otherwise you have to copy line by line of what you need from the output from ALF, and this tries to save you a bit of this work or a lot of this work. And it's definitely included together to what I said before, that if you're interested, you can talk about that later on. Right now, it's not worth taking the time to look at it. Again, it's not supported, it's just a small bash script is there. You can try to use if you want. And we can go to the last exercise, which is adding a new observable. We just saw a presentation about that. So here's your opportunity to put that knowledge in practice. I won't cover the theories also because of time, but mostly because it's been covered better than I could already today, precisely. So what you really care about is that the green functions you need are already in the code, are already provided. So you don't, I mean, this is kind of the point of ALF. You don't have to implement everything from scratch, obviously. So this is already there. What, of course, I'm jumping ahead of myself. What you want to implement here is this correlation function of the bond hopping, right? We're calling it kinetic energy for the one-dimensional Hubbard chain. Okay, so you want this new correlation function. We're gonna try to implement that. What are the code modifications? The code modifications for that. So you see it's a bit repetitive, a part of what you write in the beginning of each of exercise, because you want them to be a bit self-contained. So I hope you don't get bothered by that. So we just saw an example in the previous exercise, in the exercise 2, where we removed some of the observables. We even were allocating 5 memory for 5 before, and then it decreased that to 3. Now we're gonna make a more clean. We're gonna see the diff file is cleaner, because instead of changing or removing things, we're just gonna be, or commenting out things, we're just gonna be adding a new one. So the first modification is to go to that part of the code that allocates memory and say that you want to allocate not 5 but 6 spots in your vector, or a vector at 6 of length 6 and not 5. If you want to do the same for the time displaced observables, of course you can. It's parallel, of course. This remark is nice to know. You don't need to do it. It's not really a step to solve the exercise. It's just something that you should be aware of. That's already what's provided and what is mean in terms of green functions, so that you know that in case you want to do something different, you might need to modify this variable, and you know it exists and it's there. But you don't need to modify it here. Also, don't forget that we're going to have a background and a main part for this. You can see that in equation 5 as it's written there. And here's the observable. You see the index 6, as I was saying before. And it's going to be stored. It's going to be stored. The background is going to be stored here. Then ALF is going to take care of combining them for you. You have the reference listed here, and as it says, you can have more details about pitfalls and the physics of it in the paper, of course. And it's time to then take a look. We do have time for that, to take a look at the sort of modifications that have to be performed there. So let's go to the exercise 3. And once again, see how both plain vanilla differ. So first one, from 5 to 6 memory spots. And that means that when you have those cases, because you had, right? Case 3 spin yx, case 4 totally spin, case 5 is density. Now you just follow the pattern and have a case 6 and you tell what is the file name where this new observable that you're going to define now is going to be stored. So the file name is not only kin, but kin is the main part of it. And that's coming from kinetic energy. So, or kinetic part. So that's it for the allocated memory. If you want to do the time displaced, then of course you should mirror that in the time displaced part. So you also allocate now 6 spots, and you should say the channel is particle hold and give the file name. It can be the same file name because it's just the core of the file name, and the difference is there's going to be a tau added to it to the name of this file to show what kind of data it contains. You need a new variable JX, so you declare it. And here it is. Look, that's what I have meant with it's cleaner. The diff file is cleaner. So you're not modifying anything, you're not cutting anything, you're not commenting out anything. You're just including the calculation of a new observable. Here you do modify it a bit. Now you have to calculate. You have to join those two parts of your observable, and you can even look here at the corner where it displays where in the file the difference happened, that there's some very similar structure down there. That's going to be for the time displaced ones. So here you declare the variable you need. Now you need 2 because well, you have it in 2 positions, and then you have it again. Just essentially the same, but time displaced. And that's it. So the diff file is even simpler in this case than for exercise 2. And that would be what I'd have to say to show you about the tutorial. So as you see, I kind of I'm showing you the cheats and showing you the and giving you the hints to actually go through the tutorial. So in some sense, I took a bit of the challenge of the tutorial. I took a bit of the I hope I didn't take a bit of any of the fun of it, but I think it's I prefer I consider it important to show it in a bit more easier way, so that because we have a limited time here, so I'd like to help you guys avoid some dumb small non-relevant pitfalls in the programming, specific of Fortran, like having to declare variables and things like that. So that's why I prefer to kind of chew it a bit and make it a bit more palatable. So I hope it's of help. And as I said, in 5 minutes we're gonna have 5 minutes for questions, and after that we're gonna have yet another ALF basics. We're gonna cover. It's a very important one. It's the longest one because we're gonna cover both the models that are present already in ALF and how to build how to write your own model. And that's gonna be very helpful for the time we're gonna have then later on. I'm mistaken, I was looking at the wrong day, sorry. Today we're gonna have the interactions. Your own model is gonna be tomorrow, and that's important to work on your project, not on the tutorial. So today we're gonna have the interactions. So in 5 minutes, we're gonna have the interaction talk, and then we're gonna have some time, both today and tomorrow morning, to work on those 3 exercises, if you wish, if you can. And just like we did with the tutorial today, we're going to be here available to chat in general about ALF and physics, and of course the tutorial if you want. So please, if you have any questions, just fire them. So if everything is clear, we have a tiny 3 minutes break before the interactions ALF basics presentation. Okay.